Okay. So, good afternoon, everyone. I want to thank you all for coming out and showing interest in what I've been doing for this past semester. I want to give a couple shout outs. So thank you, Professor Vandermeer, for letting me do this. Thank you to the math department for letting me add this to my schedule. And I want to thank my family for coming here. My mom was able to take some time off of work, and my grandfather is actually up from my home state of Georgia, so he flew up the other day. So thank you for all of your support and everything. So the stable marriage problem is what I've been working on for the past semester. And what it is it's a math problem that is mostly in the field of graph theory. So it's described basically as, so imagine we get to play Cupid for the next hour. And our job is to marry individuals to their perfect mate. Now, if we had 20 people, so 10 men and 10 women, then we're given the preferences or rankings that they have for one another, then the question is, how can we create 10 happily married men-woman pairings? Or how can we create 10 stable marriages? So, careful with that. A couple definitions to start off with is that we have to define what a stable marriage is. So, a stable marriage implies, or means, that we have no unstable pairs. So, in order to have every single set of marriages that we have that has no unstable pairs is a stable marriage, or is a set of stable marriages. So, what is an unstable pair? And it's a little bit complicated just to hear it without any context, but there'll be plenty of examples in the future. So an unstable pair is a man and a woman who prefer to be with one another as opposed to the person that they are matched with. So now that we know a little bit about that, kind of get that definition in your ear. The way these work is with preference lists. So there's many different versions of the stable marriage problem, but the one that we're going to be working with is kind of the original problem, and it has to do with strictly ordered preference lists. So formally, but a little bit loosely, a strictly ordered preference list is a person P prefers a person Q to a person R, where Q and R are of the opposite sex, if and only if Q precedes R on P's preference list. So what that means is that it's basically a way that we have created this list, which every single square over here represents one of our 10 men that we're working with. All of the circles represent one of the individual women that we're working with. The numbers inside each preference list, so this is the male's list and this is the woman's list, all of the numbers inside of the lists correspond to either an individual woman for the men's list or an individual man for the woman's list. So these ranks here, they're all columns, and man number one has a opinion on every single one of the 10 women. And I'm just going to be explaining from the men's side because all of these properties hold true for both men and women. The preference lists work the same. So man number one, the woman that he prefers most is woman number 4. The woman that he prefers second most is woman number 3, woman number 1, and so on, all the way till his least preferred. So this works, like I said, for both the men and the women. And we use this to kind of state matches and get some information about the match that we picked. So a little bit of a notation here would be, you could say 1, 2, 2. So what this means is that we are looking at man number 1, and we're going to look at the match between man number 1 and woman number 2. It's important that it goes this way because it could be confused with man number 1 going to find the woman that is second on his preference list, which will not give you the same matching. So what this is supposed to be saying is that we're looking at man number 1, we find woman number 2, and we see that she is the 4th most preferred woman. If we looked at it the other way, we'd get the wrong woman because we'd be man number 1 going to the second person on his preference list, woman number 3. That's not the pair that we want. So what this 1 to 2, man number 1 to woman number 2 pair means is that 4th on the preference list, he would rather be matched with woman number 4, woman number 3, and then woman number 1, respectively. But he's happy that he was not matched with woman number 7, 6, 5, 9, 8, or 10. And now if we go over to the other side to see how this works in reverse, because everything works from the men's side as well as the women's side, we have the same match. So we go, instead, we look at woman number 2, and we find man number 1 on woman number 2's preference list, which is right here, the first preference. So woman number 2 is very happy with this match, where man number 1 is all right with it. Get rid of these. So now that we know a little bit about the preference list and we have some definitions about what we're trying to do, we know what our goal is. Oh, and also, before I talk about what our goal is and everything, it takes a long time to run through these 10 by 10, 10 women, 10 men, kind of matrix-y looking things. So we're only going to be using 4 men and 4 women when we actually go into solving this problem. So when I first started off and I heard the problem the first time, and Professor Vandermeer did a great job of explaining exactly what I was looking for. So my first thought was, if every single woman and every single man got their first choice, there could be no unstable pairs, because the unstable pair means that one of the women or one of the men wants someone more than they currently have. But if they have their first choice, they can't want anyone more than who they currently have. So I thought about that, and then I refined that a little bit and said it really doesn't matter if we're going to work from the men's side, it really doesn't matter who the women have, because if all of the men get their first choice, then it has to be stable anyways. So I was working with this idea, and when I was thinking that it's kind of rare that this ever happens, that you can ever give every single person their first choice, or you can ever give all of the men their first choice, or all of the women their first choice. But another way that I thought about it after is that, so maybe you're not getting your first choice, or maybe you're not getting your second choice. But what if we try to create the best possible choice for someone? So then I wanted to work with this idea, and I came up with a way to kind of create this, what I was hoping to do. And what I thought to do was graphically illustrate every single one of the preference lists. What I wanted to do with graphically illustrating all of the preference lists is I wanted to, this table format is it's kind of easy to read, but I wanted something that was a little clearer, that would give me more information about all of the pairs or all of the people that we were trying to match together. So in doing that, I figured that if I created this list, then it would be easy to start pulling out some inferences about the graph using some properties and things, and then maybe from that information that I had gained, I could create this match. So the way that I did this is laid out on the next few slides, but it's in pretty heavy graph theory terms. I'm not actually going to discuss the whole graph theory behind it. I'm just going to give you guys what you need to be able to figure this out, which it's not a very complicated idea. It just looks complicated when you show it like this. So going back, there was 3 steps that I wanted to take to solve this problem. The first one was the whole creating the graph. Then I wanted to draw some inferences from this graph. And finally, I wanted to use these inferences to create a matching. Now, these last 2 steps are the exact same steps that you would take to solve any math problem. We're just doing it in the frame of graph theory. So graphically creating these preference lists. And I also wrote that 4x4, or this preference list on the wall here so we can reference it. So things that we know about the problem, things that we know about the first couple preference lists, we know that every single person is connected together. So every single man has a connection to every woman on the list. So Graph Theory 101 states that every graph has to have a set of edges and a set of vertices. And we can illustrate this pretty easily by using the idea of Facebook. So whoever's got a Facebook account, you would all be considered, all of the people and all of the accounts would be considered vertices on the big graph of Facebook. And if we are trying to map everyone's friendships across Facebook, then whoever you are friends with is an edge. So we're going to kind of apply the same principle over here to our stable marriage problem. Every single one of our 4 women and 4 men are going to be vertices on our graph. And then the edges between are going to be our connections. And we're going to use these connections in a very specific manner, so that way we can fill in. They kind of are like a foundation or an infrastructure that we're then going to give some values to, so that way we can draw our inferences and create matchings. So to start off, four men. That was pretty easy. That's done. Let's make this look a little bit better, though. Okay. So now we have to be a little bit clever. We know we want 4 women. Just gonna. So we know we want 4 women. So what if we just went in and added them to our graph in the same manner as we had done the 4 men? Now, the next step would be creating these connections, adding these edges. But going back to a little bit before, we wanted this preference list. We wanted to graphically explain this preference list so we could clearly see what is happening in the graph and not just a bunch of numbers thrown at you. So if I was to draw edges from every single one of these 4 people to only these 4 vertices, it'd be pretty cluttered. We'd have 4 edges coming here, and then from 4 edges here, 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 just drawing right through the middle of the graph. You wouldn't be able to see what was going on. So we're going to do this in a little bit different way. We are going to have 4 sets of the same 4 women. Now, what we can do is we can create these edges, but man number 1 will connect to all 4 women. Here, man number 2 can connect to the same 4 women. They're just represented a little bit differently on this side. And then continue on, 3 can connect, and man number 4 can connect. So, it's looking so good. It's looking good so far. We're looking a little bit less cluttered. So let's go ahead, and what I'm going to do is I'm going to draw on these connections. This is what you would call directing an edge in graph theory. So man number 1 going to woman number 1. That will be one of our connections. Man number 1 going to woman number 2, 3, and 4. So now we have showed, or we are showing in the process of showing a way to represent every single one of these potential matches. So we're going to go ahead and do the same thing for man number 2 to all of the women, man number 3, and man number 4. So now we have every single possible match any man can have to any woman represented. Now we have to go back and do it in the opposite direction, because we want every match every woman can have to every man. So this works a little bit differently. We don't get to just draw it out this easily. It's a little bit more complicated. We're just going to go woman number 1 to man number 1. And now we have no more woman number 1 here. We put it here. So just to do the 2nd, 3rd, and 4th. So now woman number 1 is matched to every single one of the men. And we're just going to go ahead and continue filling out the preference list. So that way we have every single possible engagement illustrated. So step number 1's done. We've created our graph. Let that black marker go. I'll put it over here. Need a different color. So the next thing that we want to do is step number 2. We want to start drawing some inferences, but we don't have much so far. We have a shell of our graph with no values. So this is when we're going to go and get the meat from our preference lists. We are going to illustrate every single match and how favorable they are to a certain person. So just looking at the women's here, what I was thinking of is, what if we assigned a value to every single match based upon how favorable they are, and what if we just said that the best matches for someone were the highest values? So in this case, we have 4 vertices. So what I would do is I would say woman number 1 likes man number 2 the most. So to this connection that we have over here, from woman number 1 to man number 2, I'm going to assign that a value of 4. And now, continuing on, from woman number 1 to man number 4, less favorable match. So we're going to assign it a lesser value. So woman number 1 to man number 4 gets a value of 3. And then continuing on, woman number 1 to man number 3 gets a value of 2 because it's a less favorable match as well. So 2, and then the least favorable match, woman number 1 to man number 1, gets a 1 because it's the worst possible match. So that shows how we would go ahead and start adding these weights here to all of our possible connections. Now I'm going to go ahead and just fill in the men's. I'm going to fill in men number 1, and I'm going to fill in men number 2 using that same strategy, and then we can see, and then we'll fill in all 4 of these, or all 3 of those, and we can see how, or we'll see what I'm going to be explaining in the next slide with what we're going to do with these inferences. So further this one over is the man's preference list. Man number 1 likes woman number 4 the most. So we're going to go back and we're going to use a different color. Let's use blue. And man number 1 likes woman number 4 the most, so gets a 4 there. Man number 1 likes woman number 3 next, or it succeeds. So we're going to give a 3. Man number 1 to woman number 1 gets a 2. And then man number 1 and to woman number 1 gets, or woman number 2 gets a 1. So now going back to fill in this side of the graph, we're going to have to look at woman number 2, woman number 3, and woman number 4. And when we look at these 3, we're going to go ahead and we are going to find where man number 1 is, find how much she prefers him, and then that will allow us to determine what the weight we're going to give to this pair is. So woman number 2 and woman number 3 like man number 1 the most. So we will assign this a weight of 4. And woman number 4 likes man number 1 the least. So weight of 1. We would continue and do this for the whole graph, but I have already done so. Just save some time. And this algorithm right here actually explains how we just did all of these, how we assigned all of these weights. So we could check and see if I've done this correctly, but the red represents the connection from the men to the woman, and then the blue represents the connection from the woman to the men. So we've got 2 and 1, 1 and 4, 3 and 4, and then 4 and 1. So it looks like we did it correctly. All right, let's go over here. Uh-oh. Okay. So we're almost done. We have every single piece of information that we can add to this graph. We have all the inferences. So now, all that's left to do is to draw the matching. So what if we were to think of, we know that this number represents how much every man likes every woman and every woman likes every man. So what if we changed the way that we were thinking about this just a little bit, and we called this the most desirous, or that these numbers represent how desirous this relationship is. And if we took if we took the largest values for how much it is desired, then they should be all of the best matches. So what I did here is I just took the sums to find out how good every single match could possibly be. So 2 to 1, adding them together is 3. 1 to 4 gives you a 5. 3 to 4 is 7. 4 to 1 is 5. 1 to 4 is 5 again. We have a 4, another 5, and then a 6. So 2 to 2 is 4. 4 to 1 is 5. 2 to 1 is 3. And then we have a 5. And last we have a 5, a 4, 6, and then an 8. And hopefully I didn't mess up in any of that. Simple addition. It's been known to happen. So now, looking for those most desirous matches, highest values, you can see highest value in the whole graph is this 8 right here. So that means that out of all of the pairs, this one should be the best pair to match. So if this is the best pair to match, then it's definitely a match that we want to have in our final result. So when we match these two together, we're going to go, right, 4 is matched to 4. And now what we're going to do, every man can only be married once, every woman can only be married once. So woman number 4 is no longer available to be engaged to, and man number 4 is not as well either. So imagine that this is all gone. Also, every single one of these vertices does not exist anymore, so we can even cross out these sums. Next, we're going to look for the next highest value of how much they desire one another. So it would be 7. So we're going to make that match as well. So we have 1, 2, 3. Man number 1 matched to woman number 3. This half of the graph is gone. Cross out woman number 3 here and woman number 3 here. Now, we have a little bit of an issue that really isn't that big of an issue. The next highest value is 5. It's a tie. But fortunately for us, it's a tie between 2 different people. So our tie here is from woman number 2 to man number 1, and then woman number 3 to man number 2. So we're actually done. We're going to match these two. So we're going to have that's covered a little bit, but that's okay. So all of that work just to get these 4 numbers. This should be our stable matching if all of our assumptions about what we were doing are valid. Cool. This slide, this algorithm just shows how I had created all the matchings and how I took the sums and everything. So it may not be obvious that if every single preference list has a stable marriage, but we invented this thing, so we can definitely check for it. The way that we do this is these underlined values here are these pairs that we just found from the algorithm. So now, the way that we can do this, let's put this back up. Is that we're going to check for this unstable pair that I said that there would be an example of earlier. Hint, hint. So, starting off, this algorithm tells us what we're going to do here, but what we do here is that man number 1 would rather have woman number 4 than be married to woman number 3. So we're going to go ahead and we'll just check out woman number 3, or woman number 4. Woman number 4 was matched with her first choice. So woman number 4 doesn't want to be married to man number 1. So this match is out. Doesn't matter. Stable so far. Continuing on, man number 2 would like to be married to woman number 3 over woman number 1. So we're going to go ahead and check woman number 3, and woman number 3 got her first choice as well. So she could not possibly want to be married to man number 2. The next one goes back to woman number 4, and we already know that woman number 4 got her first choice, so we're set there. Still stable up until the last pair. So let's see what happens here. So man number 2 wants to be married to woman number 2 over woman number 1. Unfortunately, we have a little bit of an issue right here. Man number 2, or woman number 2, is currently married to man number 3. And this is open. So this pair right here from man number 2 to woman number 2 is unstable. And what this means is that we have no stable marriage. So unfortunately, I didn't get published or anything. But it's all right because we learned a lot about how these preference lists work. Over here. And it helps us when we actually learn the real math of what's going on here. So these preference lists are really important, and like I said before, it may not be obvious that there is a stable match every time, but this algorithm will actually generate a stable match every time, unlike what I was thinking with trying to pair everyone to their best match. So the way this algorithm works is that we go through a proposal sequence, or a round of proposals. Every day is one round, and then the way our days work is that in the morning, every single man proposes to his favorite or his most preferred woman. In the evening, the women will accept proposals from their most preferred suitor. Now we can see, this is relevant if a woman received more than one proposal from a man during the morning. So a woman will then reject whoever is her lesser preferred suitor, and then the rejected suitors will propose to their next most preferred woman on the following day. This sequence continues until every man is engaged, and upon termination, we have a stable marriage. So this is how this works. That's what I'm looking for. This time we're going to go through the algorithm, but it's pretty quick because we know how the preference lists work. So a little bit of background about how we do this. So line number 1, we're going to start off and say assign each person to be free. This is kind of a little bit of a maintenance type deal that we're just making sure that we're going to reset the whole preference list of any possible matches that could have started by accident, so the algorithm runs smoothly. Now, what this means, while some man M is free, while there's a man that's not engaged, we're going to run through everything that's in here. So, start off, assign each person to be free. then we go into our while loop. And the first step of our while loop is W with a funny looking symbol that goes to the first woman on men's list. What this means is that we are looking at the first woman on a man's list, and we are going to then propose and become temporarily engaged to this woman. So coming up, yellow means a temporary engagement. This is basically starting off on day one, and this is what basically happens in the morning of the little intro that I just talked about. So man number one proposes to the first woman on his list and gets accepted. Man number two does the same, along with man number three. We now have an issue, though, when man number four proposes to his most preferred woman. Oh, before I finish this, has everyone done their cards? Okay, so if you would like to be in our celebrity matching here that we're going to do, and you can find out who your celebrity mentor is, then I can take all of the cards and we'll get this going. So whoever wants to. Only 9 people can participate, yeah. A famous match. Of course. Okay, we have 5. We need 4 more. 1. Yeah, put your name on it. Oh. Okay. We have a lot of people. Oh, all of them without names. Perfect. It's okay. Randy has his name. All right, how many do we have? 1, 2. You got. Okay. Sorry. Yeah. Okay, so we have our issue here that a woman can only be engaged to one man. So we go into this next part of our algorithm, which essentially says that the man that she least prefers just gets rejected. And then when he gets rejected, he is now free. No temporary engagement there. So we go through, and the way this whole Gail Shapely works in total is that every man gets his best possible option, and then every woman will get her worst possible option. So what this is going to mean is that in order for her to get her worst possible option is every temporary engagement she has will bring her closer to the top of her list, where every failed engagement here will make every man have a worse possible engagement or be married to a worst possible least favored woman. So we freed this man, and then because of the fact that women can only trade up and men can only trade down, I guess you could say, we're going to delete every single other possible men pair. So we have a free man now, so we've got to start over. Man number 1 proposes to his next most preferred, the next most preferred woman on his list. So when he did this, the same situation as before. We had a tie again. So the same thing happens. The man is rejected that was beforehand, that was preferred less, and then we deleted every possible woman that was to be matched. So we have another free man, goes ahead, and it continues, where we get another person that was engaged to, or another woman that is now engaged to more than one man. So we go through again, and woman number 2 preferred man number 2, who is the engagement from right here. So woman number 2 preferred man number 2 more, so she had rejected man number 3, which then means that man number 3 cannot be a possible suitor anymore. So, starting again from last time, we know that this is going to be the last time because man number 3 doesn't have any more options except for woman number 1, and this works every time. So if you don't have a stable marriage at this point, then you messed up somewhere in your algorithm, or when you were executing the algorithm. So man number 3 does his proposal to woman number 1, and woman number 1 gets a proposal. And we now have all of our temporary matches created, which now form what we hope to be, if we didn't mess up, a stable marriage. So let's go back. That's not what I wanted. This is what I had. Okay. Cool. So, Gale-Shapely, or Gale-Shapely algorithm, will give you that stable match every time. My algorithm, unfortunately, did not. We can test Gale-Shapely to see if this is indeed a stable matching by going through that same process that we had with the algorithm I created. So first off, man number 1, if we were to check this, then we'd have man number 1 would rather be matched with woman number 4 than woman number 3. So going down, checking the pair, woman number 4 got her first choice, so they don't want that matching. Woman number 3 got her first choice as well. So man number 2 cannot be matched to woman number 3, as well as 4, first choice again. Now, here is the match that was created that my algorithm did not have. This 2-2 pair here was shown, and it was actually put into the matching with the Gale-Shapely. Now, unfortunately, this doesn't mean that the blocking pair or the unstable match that we had here will always be included in the Gale-Shapely. This was just coincidence that this match was placed in. Also, with the Gale-Shapely, the matches we got were 3-2, 1-4, and then 3-2, 1-4. That's also a coincidence. It doesn't just go numerically through the list like that every time. So, the fun part. the celebrity mentor. We're going to go ahead and do another one of these Gail Shapely's quickly. And we're going to match everyone to their favorite celebrity. So a lot of people like Albert Einstein the most. Then there's some Steve Jobs, Ben Franklin. Okay. So Trey, man number one, or person number one, his favorite is Albert Einstein. So what we're going to do is we're going to, temporarily match. Trey is temporarily matched to Albert Einstein. Kurt also wants Albert Einstein. Kurt is person number two. So Kurt now gets matched to Albert Einstein, and unfortunately, Trey does not get matched to Albert Einstein. So we're going to remove there. Randy, next person, person number three, wants to be matched to Albert Einstein as well, so we know that that one didn't work out. Albert Einstein got his first pick. Bill wants to be matched to Ben Franklin. Bill is person number four. So last choice, but you're in right now. James, person number five. It's Ben Franklin, his first choice. Let's make this a little easier. So James cut out Bill and is now matched to Benjamin Franklin. John Doe, number six. Was that a SJ for Steve Jobs as well as the other ones? SJ is... Oh, Scarlett Johansson? Scarlett Johansson. All right. So John Doe, number six, wants Scarlett Johansson the most. So we circled the six. And then John Doe, number seven, wants Steve Jobs. So Steve Jobs, number seven, right here. Ashley, Steve Jobs as well. Ashley is number eight, so unfortunately Ashley did not get to be matched with Steve Jobs, and Rachel wants, where's this be? Sandra Bullock, okay. Rachel wants to be matched with Sandra Bullock, and for now, yes. You get the match. So now, day two, we move on to the people that were rejected on the first day. So starting off, we're going to match Trey to Robert Downey Jr. So Trey is man number one. Kurt already has his match, so we had to skip him for now. Randy wants to be matched in his second iteration to Benjamin Franklin, and Benjamin Franklin likes Randy more than he likes James, unfortunately. So now we go and Bill. We match Bill, and Bill wants to be matched with Albert Einstein, but unfortunately Albert Einstein is already matched, so that's not a possible match. James wants to be matched to Albert Einstein, which is also not possible. Albert Einstein has his most preferred celebrity student, or student, professor. John Doe, number six, wants to be matched to Benjamin Franklin. And no. Oh, already matched, yes. I make these mistakes often. Ashley is the next one that's unmatched, and Ashley wants to be matched to Sandra Bullock. Yeah. So yes. Number 8. Oh, just slightly V. Okay. Day 3 starts. And we start with Bill, because Bill is the first one that's unmatched, I believe. Yeah. Bill wants to be matched to Steve Jobs. Steve Jobs already has a match, so Bill gets rejected a third time, unfortunately. James would like to be matched to Steve Jobs as well, so James actually wins. James gets matched to Steve Jobs. And number 7, John Doe number 7 is now removed from being matched with Steve Jobs. Next open match we have is Steve Jobs, but that one was just rejected. So, we still have one more from this list. Okay, so Rachel. Rachel would like to be matched as her second preference with Emma Watson. So far, Rachel gets Emma Watson. This is like day 3 or day 4 now. Day 4 is over. Oh, what did I do? Oh, 9, yes. See, I told you, thank you. Okay, so we're good for this day. So now, first unmatched proposer is Bill. Bill now wants to be matched with Robert Downey Jr. And yes, it's rejected again. Now, John Doe number 7 was matched with Steve Jobs, and that was rejected. So now I'd like to be matched with Leonardo DiCaprio, who has not been matched yet. So number 7. All right. Now we get to go back to Bill because everyone else has their match. So Emma Watson now. Bill is number 4. Bill gets matched with Emma Watson finally. And Rachel is rejected. So Rachel then wanted Albert Einstein, who was matched to their most preferred. And then following wanted Benjamin Franklin, who was also matched to someone more preferred. But Robert Downey Jr., you get matched with Robert Downey Jr. And person number 1 has lost that match. So now Ben Franklin, person number 1. Oh man, mixing things up at the end. Matches with Ben Franklin, person number 3. So Randy, Emma Watson, that match is not possible. Robert Downey Jr., not possible as well. So we're down to Scarlett Johansson, which you get matched with Scarlett Johansson. And person John Doe number 6 is unmatched from Scarlett Johansson. Ben Franklin again is already taken. SB Sandra Bullock. John Doe number 6. Oh, and this match is created. Sandra Bullock. Sandra Bullock rejects person number 8. So Ashley now wants to be matched with Emma Watson, which is not available. LD, Leonardo DiCaprio, also not available. Preferred least. Scarlett Johansson again. Where are we at? 8? Scarlett Johansson. No, not matched. Ryan Gosling. Ashley completes our Gail Shapely by being matched with Ryan Gosling. So our final matches that Professor Mandervale is circling would be Trey is matched to Benjamin Franklin, Kurt is matched to Albert Einstein, Randy is matched to Steve Jobs, or Scarlett Johansson, done that so many times. Bill is matched to Emma Watson. James is the one that was matched to Steve Jobs. John Doe number 6, matched to Sandra Bullock. Yeah, Sandra Bullock. John Doe number 7, matched to Leonardo DiCaprio. Ashley gets matched to Ryan Gosling, and Rachel gets matched to Robert Downey Jr. So that's essentially how our Gale-Shapely algorithm works. Yes. Oh, right here. Now just a couple quick things about the Gale-Shapely algorithm that's a little bit interesting. So no matter how you do it, or no matter the order of the men that are proposing, every single execution of the Gale-Shapely algorithm will give you the same result. And when the men are the proposers, the algorithm promotes the best possible man, or every man gets their best possible match, and every woman gets their worst possible match. So it's a little interesting because it actually gives you a bound on where your stable marriages can be found. So there was a proof of that no matter what the order is that the men are proposing, that the algorithm is the same. But a little bit more interesting here is that in the blue, I've done the Gale-Shapely algorithm for men as proposers, and then in the red, I did the Gale-Shapely algorithm where the women are the ones that are proposing. So the way that it worked was that men proposing, they get their very best possible match, and then when the women were going through with the men proposing, they got their worst possible match, represented in blue. And now, if you flip it around and let the woman propose first, and the men will be the accepting, the women get their best possible match, and the men will get their worst. Now, the orange here is where the men proposing first and the women proposing first actually came up with the same match. So in spots that it's orange here, there's actually one possible match for that entire pair that can be matched in every single version of doing any stable matching problem ever. So in our 4x4, there's like 16 possible matches, and it's possible that out of all 16 of them, only one is a stable match. So there's a couple other problems that go along with this Gale-Shapely and stable marriage problem type deal. So you can add in a thing called indifference where, just for example, what if Trey didn't really care if he got Albert Einstein, Robert Downey Jr., or Benjamin Franklin as his match? What if he wanted all three of them the same, wanted all three of them the most? There's a way that you can do that, and it's actually a pretty interesting problem of how you do that. You can add in partners that are unacceptable. So going back to Trey, what if Trey said, absolutely no, I will not be matched to Emma Watson, Steve Jobs, or Sandra Bullock? There's a way we can solve that too. The stable roommates problem is another extension, and then the hospital residence problem actually uses the same algorithm that we put online, the Gale-Shapely algorithm, and it matches graduate students, the graduate students in med school, to their residencies, and this is used today still. Stable roommates problem is not solvable, and the hospital residence problem is solvable except for a situation where couples would like to be matched together and the couples would like to go to the same hospital. So, thank you for your time this afternoon. Coming to learn about this. I can take any questions that you may have. Okay. The runtime is okay. I'm not that familiar with exactly how the complexity analysis works, but I do know that it runs in n squared, which I'm pretty sure that's a long time, but it's just barely solvable.
Well, but it's
Yeah, it is. It's polynomial, where the stable roommates is NP complete.
So the next question would be, so does eHarmony use this?
No, I knew that would come up. I don't think so. But when I was doing this, I may have came up with a few ways that I could possibly implement this into some kind of algorithm. It's all hush-hush, though, so when I get famous one day, you guys can all say you knew this person. Any other questions?
If you consider more men than women situations,
Yes.
that is square matrices.
Yes, I'm pretty sure that that problem, it's not something that I focused on, but I'm pretty sure that that problem falls under the whole unacceptable partner range, and it's not as well discussed. We used we used this book here from the MIT Press, and they talked about it briefly, but it wasn't discussed that much, so it's this book.
Does the algorithm also work for non-square matrices?
It does sometimes, not all of the time. It depends on a lot of things, and I'm not as familiar with that part of the problem, so I'm not sure if it works ever. Like, I know it doesn't work every time, but I'm not sure how often it works, what will make it work, and what it doesn't work for, and those kinds of things.
Any other questions? Grant, thank you. That's excellent.
Yeah. Thank you. Thank you.
Grant will stick around for a couple minutes afterwards if you have other questions or comments. Thanks again for coming. Our next talk will be late January 4th.